In this video, we will talk about stoichiometry. Stoichiometry, as given as Stoichiometry, it's a Greek word meaning counting of elements, or rather, in our context, counting of chemicals in a chemical reaction. We have a chemical reaction such as aluminum reacting with oxygen gas, that is, to give us aluminum oxide. We can do stoichiometry on this. Before we carry out this reaction in the lab, we need to know how many grams of aluminum or how many grams of oxygen to take so that they can react together in the right amounts. The very first thing we need to do is balance this equation, and balancing an equation means putting a coefficient before each of the chemical reagent. And if we balance this correctly, we will put a 2 here because there are two aluminums on the right side. We want to turn the smaller number on one side equal to the higher number on the other side. So aluminum on each side should be 2 here, and notice that I have 2 oxygens here but 3 here. How can I balance that? So what is the most common smallest multiple of these two? It's 6. If I had 6 oxygens on the one side, then I can have 6 on the other side. So in order to balance that, I would put a number here, and that number would be 2, right? 2, because now 2 times 3 is 6 6 oxygens. But notice that changes the number of aluminums now. Now we have 4 aluminums, not 2. So what do? We have to change this here from 2 to 4. That will be 4 aluminums rather than 2, and that's the 4. So 4 aluminums on each side, and finally when I put a 3 here, now the reaction is completely balanced. So before we start our stoichiometry journey, we need to balance equations completely, right? So 4 aluminums on the reactant side on the left of this arrow, 4 aluminums on the product side, 2 times 2, 4. 3 times 2, 6 oxygens on the reactant side, and 2 times 3, 6 oxygens on the product side. Now here is a question. What does this balanced equation mean? It means that 4 aluminum molecules, or atoms in this case, because aluminum by itself is an atom, not a molecule. So 4 aluminum atoms react with 3 molecules of oxygen gas to make 2 formula units of aluminum oxide. Okay, because it's a ionic compound, we don't call it a molecule, we call it formula units because it's a simplest whole number ratio. But the best way to read this is in moles. 4 moles of aluminum react with 3 moles of oxygen to make 2 moles of aluminum oxide. Now if I said how many moles of oxygen would be required if we had 7.5 moles of aluminum? Well, if I had 7.5 moles of aluminum, what I would do is make a conversion factor from the information from the balanced equation, the ratio of the number of moles of aluminum to oxygen, and write it in a way such that the moles of aluminum cancels out, putting it in the denominator. 4 moles of aluminum there for every 3 moles of oxygen here. And when you do the math, make sure you know the math to the correct sig fix. Now the numbers 3 and 4 are not measured numbers. They are obtained from the coefficients of the balanced equation. Hence they have infinite sig fix. They are exact numbers. The only limitation here is the 7.5, which is a measured number. Somebody had to measure 7.5 moles of aluminum, and when we do the math to the 2 sig fix we should have, we end up getting 5.6 moles of oxygen, right? So 5.6 moles of oxygen would be required to react with 7.5 moles of aluminum. This is very simple, going from moles of one reagent to the moles of another reagent according to what our balanced equation gives us. The most you could be asked to do is go from grams of one reagent to the grams of another reagent. What do I mean by that? Well, keep the same equation, but let's assume that we are given grams of aluminum. We are told that we have, let's say, 21.3 grams of aluminum in our possession. How many grams of oxygen gas should we use for this reaction? In this case, all we need to do is convert the grams to moles, and then that is the moles of aluminum, and then we already know how to go from moles of aluminum to moles of oxygen. And then if we are required to go from the moles of oxygen to the grams of oxygen, that also we can do. This extra conversion between grams and moles will require the molar mass of the reagent that is under question. So here we have aluminum. To convert the grams of aluminum to moles of aluminum, we need the molar mass of aluminum. What is the mass of 1 mole of aluminum? We write that in the conversion factor form. You can search it out online, but if you have the periodic table, you can simply use the periodic table and add up all the elements within the compound, and it turns out that the molar mass of aluminum to 2 digits after the decimal point, let's keep 2 digits, don't have to write down every digit, it's 26.98 grams, right? If I was to do this calculation, grams of aluminum would cancel out, leaving me with the unit of moles of aluminum. Of course, I had to run the numbers in the calculator as well, but we won't stop here. We will stack our next conversion. Now that we know that this gives us the moles of aluminum, we convert it to moles of oxygen by using the molar mass ratio between aluminum and oxygen, and write it down in the way that the moles of aluminum here will cancel out with what we write here, which should be sorry, 4 moles of aluminum, and here it should be 3 moles of oxygen. Where did I get this number from? We got it from the balanced equation coefficient. So mole of aluminum, those are our units cancelling out. And if I was to stop right here, I would end up getting the moles of oxygen, but I don't want to stop. I'm going to stack one more conversion factor. This will take us from moles of oxygen to grams of oxygen. So 1 mole of O2 weighs how much? It weighs 32.00 grams. The way I wrote it makes us cancel the moles of oxygen, and then we simply process this out, and we get, we are limited by 3 sig figs in the original number 21.3. Make sure you plug everything correctly in the calculator. And I get 18.9 grams of oxygen. That's how much oxygen would be required for us to react these two. What does it mean to have 21.3 grams of aluminum and 18.9 grams of oxygen? It means that if you have those amounts for both, they will completely react with each other. At the end of the reaction, there would be no aluminum remaining and there would be no oxygen remaining. But let's think for a second. What if I started with more oxygen? I took the same amount of aluminum, 21.3 grams of aluminum, but I took 50 grams of oxygen. What will happen then? Well, until we use up 18.9 grams of oxygen, the reaction will go as expected. But after that, there will be oxygen remaining, but we will run out of aluminum. Without the two of them being present, there is no reaction. And so we would not be producing any more product at that point. And we say that the one we ran out of, in this example of using 50 grams of oxygen and 21.3 grams of aluminum, we run out of aluminum and we say that aluminum is the limiting reactant. Okay. On the contrary, let's say I took 18.9 grams of oxygen, but I took 50 grams of aluminum. In that case, I run out of oxygen with aluminum remaining. I would say that in that case, my aluminum is, my oxygen in that case is the limiting reactant where I ran out of aluminum. I'm sorry, again, 50 grams of oxygen and 21.3 grams of aluminum. In that case, we run out of aluminum and oxygen remains, so aluminum is the limiting reactant. On the other hand, if I had more aluminum, then this ratio of 21.3 grams of aluminum and 18.9 grams of oxygen, if I had 50 grams of aluminum, in that case I would run out of oxygen and oxygen would be the limiting reactant. Finding out which is the limiting reactant is very simple. Either you can see how much product you make. For example, if I had 5 grams of let's say 5.0 grams of aluminum, how much aluminum oxide can that give me? Either in grams or moles, doesn't matter. And then let's say at the same time I had 7.0 grams of oxygen, how much aluminum oxide that can give me? Okay, just like this process here, going from grams of oxygen to moles of oxygen, from moles of oxygen to moles of aluminum oxide. We can stop right there or we can go all the way to grams if we care about it. Whichever gives you the less number of grams of the product is the one that is your limiting reactant because it ran out at that point. So it can be very easy to find limiting reactant in multiple ways.